All right, let's start into chapter 3. So in this chapter, we're going to begin our study of differential calculus. And so what differential calculus is, it's concerned with how one quantity changes in relationship to another. So this is an outgrowth of the velocities and slopes of tangents that we talked about in chapter 2. So maybe it'll help solidify what that was talking about if you weren't quite sure. And after learning how to calculate derivatives, we can use them to solve problems involving rates of change and approximation of functions. So 3.1 starts with the derivatives and rates of change. And we're going to look at all these different things. These notations are very important to us. We're going to be using them the rest of the time in calculus. So let's start by looking at tangent and secant lines again. So first of all, these aren't tangent lines. But if we want to look at the tangent line at the point 1, 2 of this, so it looks here, and as we zoom in closer and closer to that point, it's going to look more and more like a linear equation. And so that's the point. Our tangent lines, it's going to be a linear equation at that point, but we started by finding the slopes of the secant lines. And to start that, we're going to look at the equation right here for the slope. We're going to estimate the slope to this line at 1, 2, and we're going to look at 0.9 and 1.1. So when x is 0.9 and when x is 1.1. So we do change in y over change in x. So the y values, notice right here, I know it's hard to see, but it's 2.431 and then minus 1.629 all over 1.1 minus 0.9. And that gives us 4.01. So we think it's probably going to be around 4, but let's get even closer. Remember, that's what we did. Each time we got closer and closer to see what it looked like. So 2.0403 minus 1.9603 all over 1.01 minus 0.99, and that gives us 4. So 4 is probably going to be it. So these were just estimates though. Now we're going to look at how to find it exactly. So let's find it exactly. We're going to use this. The limit as x approaches a, so as it gets smaller and smaller, of f of x minus f of a. And so let's look. If a equals 1, and then our function is x cubed plus x. So the function x cubed plus x, that's f of x, minus f of a, we're just going to plug in a for those, so a cubed plus a all over x minus a. Now we're going to let x or a equal 1, so I'm going to go through and I'm going to erase all my a's. I'm going to put a 1 in for those values, and I'm going to get x cubed plus x minus 2 over x minus 1. Now if you remember back to Algebra 2 and Pre-Cal, you can do synthetic division here. Let's see if it comes out. So put a 1 in the box, and then across the top I'm going to put a 1. I skipped an x squared, so I need a 0, a 1, a negative 2. And so dividing, I get a 1, 1, 1, multiplied 1. This is a 2, because 1 plus 1 is 2. 2 times 1 is 2, 0. So it was a factor of it. So it factors the numerator as an x minus 1. And then this is going to be an x squared plus x plus 2. X squared plus x plus 2 all over x minus 1. Notice it shares a common factor. That'd be a hole in the graph. And then it reduces down to x squared plus x plus 2, which tells me now that I want to plug in the point 1, 2. So x is 1. So 1 squared plus 1 plus 2, that's going to give me a 4. So my slope is 4. So to write the equation, I'm going to use the point slope form. Y minus y sub 1. And my point that I was using was 1, 2. So y minus 2 equals 4 times x minus 1. So distribute the 4 Move the 2 over. My equation of the tangent line there is y equals 4x minus 2. So another way we can express the slope is this, and this should be familiar. This is the difference quotient that we've talked about. So it's f of a plus h minus f of a all over h. And we can do it that way. So we can do the f of x minus f of a all over x minus a, or we can use this. And we can express that this way. So we want to find f prime of a, and that's equal to the limit as h goes to 0 of the difference quotient. Now, this right here, all that is the derivative. So we're finding the derivative. So we need to find the slope, first of all, and then find the equation of the line. So let's start here. I need to find f of a plus h, so that's 1 over a plus h squared plus 1, minus f of a, it's 1 over a squared plus 1, all over h. Now, this is where it's going to start getting into really paying attention to if you know your Algebra 2, if you know your pre-cal, because we have to simplify these. We can't just do this and leave it. So I need to get a common denominator here. So I'm going to multiply it by the other denominator. So a plus h squared plus 1. What I put on the bottom, I have to put on the top. And then on the other function, I need to multiply by the other denominator, so a squared plus 1. And at this point, I'm not going to simplify the whole denominator, but I am going to simplify the red part. So I'm going to get a squared plus 1 in the numerator, and a squared plus 1 grouped down here. Now, the red part here, I'm going to multiply. It's going to be an a squared plus 2ah plus h squared, and then this plus 1 I'm going to go ahead and put in there with that. So that's my whole denominator. It's the same on both sides because I multiply the same things together. So I need to subtract this group right here, and I'm going to do the same thing that I just did in the bottom because it's a minus h squared plus 1, so that's a squared minus 2ah plus h squared plus 1. Now I need to be careful because I messed up a little bit. Up here, there should be a plus h in there, so that's a plus. I've got to subtract them. And I get a squared plus 1 minus a squared minus 2ah minus h squared minus 1. And a lot of stuff's going to cancel out here, which is nice. Well, maybe not a lot, but enough. And then I get, on the bottom, I'm just going to carry it along as it is, a squared plus 1, and then a squared plus 2ah plus h squared plus 1. And it goes to negative 2ah minus h squared. And what I have been leaving out up until this point is that it's all over h. I'm going to scroll back up here in a second and show you, because I needed to simplify everything that I could as far as I could first. So if I look back up here, my difference quotient here is that all divided by h. So I'm going to go down here and now put it right here, because the divided by h, it was in the bottom, it was in the denominator, so I just put the h in the denominator. And I'm going to reduce. I could have factored out the h right here this way and then just canceled those. That would have worked as well. That helps a little bit, makes it a little nicer. And so I'm down to the function negative 2a minus h over a squared plus 1 a squared plus 2ah plus h squared plus 1. Now, it said it was the limit as h goes to 0. So as h goes to 0, we found out because it's a rational function, I can just plug in the 0. And so that means if this is 0 here, this one's 0, this is 0. Those terms are all gone, which leaves me with negative 2a over a squared plus 1 times a squared plus 1. Guess what, guys? I'm just going to show you this. Negative 2a over, this is an a squared plus 1 squared, which is kind of neat. And then it wanted when scrolling up here, right here, when a is 0, because that's what your x value is. So I want to know when a is equal to 0 what this value is equal to. So I'm going to plug in a 0, negative 2 times 0, all over 0 squared plus 1 squared. That's equal to 0 over 1. I need to make sure it's not a 0 in the denominator, so it's equal to 0. So my slope, when a is equal to 0, is 0. Yeah, all that work for getting a 0. So your slope is 0. Now we need to write the equation of the tangent line at the point 0, 1. So y minus 1 equals 0 times x minus 0, because slope's here. This 0 goes in there. And I get y minus 1 equals 0. So the equation of the line, the tangent line at the point 0, 1 is y equals 1. And if I look at the graph and I go to the point 0, 1 right here, that would make a lot of sense because it's going to be a horizontal line going through 1, so it's y equals 1. Now let's look back at the graph a little bit and see what we can tell about derivatives and slopes and tangents and all that stuff from our original function. So here is the function y equals sine of x graphed, and I want to estimate the slope at 0, 0. So estimating the slope at 0, 0, I'm going here. Remember, it's tangent there. And so what do you think? What do you guys think that would be about? So tell me here in a second. I'm going to leave that up as a question in the middle of this. And then B, I need the slope at pi over 2, 1, which would be up here. You tell me what that slope you think it would be. C at pi 0, what do you think that slope might be right there? And then D, it's going to be pi over 3, and then square root of 3 over 2. What do you think that slope might be? So just thinking about that, what do you think happens to the function when the slope of the tangent is increasing? So when the slope is increasing, what do you think is happening to the function? Well, it's going up. It's increasing. So when the slope is decreasing, what do you think happens? When the slope is 0 for that tangent, what do you think is going on? And what about when it's slowly changing? There's different changes here. Notice the purple line that was drawn versus the black line that was drawn. This is a quick change, and then the black line here was a slower change. Think about that. We'll talk more about that tomorrow in class. So just pulling this together from the last section, our average velocities is the displacement over time right here, and it's slopes of secant lines, where h is that difference from the one point to the other, how far apart they are. And when the time difference gets smaller and smaller and smaller and smaller to where there is no change right here, it's an instantaneous velocity. And that instantaneous velocity is the slope of the tangent line. And hopefully you're paying attention to the difference, is that this limit is in the front, whereas up here it's not. Now we're going to look at how this can apply in some everyday situations. So suppose a ball is dropped from an upper observation deck at the CN Tower, which is 450 meters above ground, and we want to know what the velocity, the instantaneous velocity of the ball after 5 seconds is, and then how fast the ball is traveling when it hits the ground. So we're going to use this equation, and we're going to use the difference quotient to figure out what it would be when h goes to 0. So we're going to go, our derivative, f prime of a, that's the derivative notation, is equal to 4.9, and then in the t, we're going to put in a plus h squared minus 4.9 a squared, because it's the a minus h minus the a all over h. We're going to simplify this. And remember, we're going to find it as h goes to 0, but we need to simplify first. So this is 4.9. This is going to be an a squared minus 2ah plus h squared. And this is just 4.9 a squared all over h again. Now, I could distribute this through, but I'm not going to, because I'm going to notice something right here. This 4.9 a squared and that 4.9 a squared will cancel out. And I'm left with 4.9 times this plus this is a 2ah plus h squared all over h. Now I can cancel out 1 as long as I cancel out on each thing. So this is 4.9 times 2a plus h. Remember, h is going to 0, so in this h, this is 0, so this is actually just 4.9 times 2a, which is equal to 9.8a. And we want it when the time a is equal to 5 seconds. So we're going to plug in a 5 there. So this becomes f prime of 5 is equal to 9.8 times 5, which is 49 meters per second. So it's traveling after 5 seconds at a rate of 49 meters per second. Now, if we look back up here, B says, how fast is the ball traveling when it hits the ground? Well, it's going to hit the ground after it drops 450 meters. So the height, the distance that it's gone is going to be 450. So 4.9 t squared equals 450 because it's gone 450 meters. So don't be distracted by that. We're going to divide by 4.9. T squared is equal to 450 divided by 4.9. Take the square root of both sides, and t is equal to 9.6 seconds. So in 9.6 seconds, that's when it's going to hit the ground. So now we go back and use our derivative that we just found. F prime of a equals 9.8 times a, and the a this time is going to be 9.6, and that gives us approximately 94 meters per second. That's how fast it's traveling when it hits the ground. So just from doing this problem, you can tell that physical situations can be translated into statements about derivatives, because we just did one, and that was about the ball dropping and what the derivative stands for. So here's some examples. The budget deficit can be viewed as the derivative of the national debt. So the national debt is in dollars, and so the budget deficit, for example, is measured in dollars per year. So the budget, the deficit is calculated every year, so it's money. And then another example, S of D, represents the sales figures for a magazine given D dollars. And so then D dollars of advertising. S is the number of magazines sold, and the derivative is the magazine sold per dollar spent. I'm hoping maybe you're starting to see a little pattern here. Let's look at one more. Example 3 is that S is equal to the function t. It's a position function of a particle that moves along a straight line. So it's position at time t. And then the derivative, f prime of a, it's the rate of change of the displacement with respect to time. So it's change in distance over change in time. So hopefully you're seeing a pattern here. And you can tell me what pattern you're seeing in this question right now. So what we've looked at is we have seen that the same type of limit arises in finding the slope of a tangent line or the velocity of an object. In fact, the limits of the form right here, as h goes to 0, of the difference quotient. So the derivative of function f at the number is denoted by this. And I've been using it some, but it's equal to the limit of the difference quotient if that limit exists. And again, you can write it in this other way, but most of the time you see it this way. So find the derivative of the functions here. I'm going to do the first one, and then I'm going to leave the second one for you guys to do and leave it as a question at the end of this for you to tell me what you got. So here we go. I want to use it as the difference quotient, f of a plus h minus f of a all over h. And so what I get is the square root of 1 plus a plus h minus the square root of 1 plus a all over h. And so when I see this, I'm going, okay, what do I need to do here? There's nothing in the denominator. There's not fractions and fractions. So I'm going to have to multiply it by the conjugate because I can't divide by a 0 because we need to get that h to be 0. So I'm going to multiply by 1 plus a plus h plus the square root of 1 plus a. So the conjugate changes the sign. And what I do to the top, I have to do to the bottom. 1 plus a. That's a plus a right there. Same thing. I'm not going to multiply this through in the bottom. But because the tops are conjugates, it's just the first squared minus the second squared. So that's going to give me a 1 plus a plus h minus 1 plus a all over. I'm going to leave that h out front. Square root of 1 plus a plus h plus the square root of 1 plus a. So up here, this becomes 2 minuses when that's a plus, and so that's going to cancel out right here. And I'm left with an h over h. And this is the whole reason I don't multiply that h through, is because it will almost always cancel out when we're doing this, because the whole point is it needs to go away. And remember, it's the limit as h goes to 0, so h is equal to 0, so this one's gone. And then check this out, I get 1 over 1 plus a plus the square root of 1 plus a. That's 2 of them. So I get 1 over 2 square root of 1 plus a. And we wanted to know it when a was equal to 3. Now you're like, where did that come from? Well, it came from t equals 3 right there. So it was given in the problem. So I plug in a 3. So this is 1 over 2 times 1 plus 3 is 4. So this is 1 over 2 times 2, which is 4. So that's the derivative. All right, it's your turn. You try this one. And it's when x is equal to 1 or when a is equal to 1, if you want to look at it that way. Remember, it's the function's the limit as h goes to 0 of f of a plus h minus f of a all over h. So find that, and you're going to make a equal to the 1 at the end. We've done this, but just pointing it out, when we want to find the equation of the tangent line to y equals your function, you're going to have your point. It's the line through that point whose slope is equal to the derivative of f at a. And so then to write the equation, you're going to use point slope form. And so your slope is the derivative. Just looking at this graphically one last time, because we saw it in chapter 2, but we're going to look at it again. It's the difference quotient. See, it's written all kinds of different ways, but it's still the difference quotient. It's the average rate of change of y with respect to x over the interval. So if we're looking at an interval, it's that average rate of change, and can be interpreted as the slope of the secant lines. And so the instantaneous rate of change is equal to the slope of the tangent line. So average is the secant, instantaneous is the tangent. And when that change gets smaller and smaller, we're getting our instantaneous rate of change. So when we looked at the previous slide, to get that instantaneous rate of change, we need to make that difference go down to 0. So delta x goes to 0, the change in x goes to 0, or you can look at it as x2 goes to x1. It's the slope of the tangent line, which is the derivative of f prime of a. So the derivative is the slope of the tangent to the curve when x is equal to a, or you can look at it as the derivative is the instantaneous rate of change of y equals f of x with respect to x when x equals a. So it's the tangent slope or it's the instantaneous rate of change. It's the same thing, just different words to talk about the same thing. And looking at a picture of what that means is that when the derivative is large, the curve is steep. So this is a large derivative, a large number. Your curve is steep at the point P in the figure. So your y values are changing rapidly. They're clustered farther apart. So here, here, and here. They're not clustered close together. But when the derivative is small, like the tangent at Q, the curve is relatively flat and the y values change slowly. So they're much closer together. They're clustered closer together, those y values, for the same change in the x. So that's a neat way to look at it as well. So I want you to estimate the slopes of the secant lines between x equals a and b, so from P to Q, and between x equals b to c, right here. And then I want you to order the 5 quantities. F, the derivative of f at a, so just a hint, remember that's this tangent line. The derivative of f at b, and then the derivative of f at c, and then the slope of PQ, the slope of QR in decreasing order. So give me the largest to smallest. So answer that question and tell me what you think. What's the largest? And then all in the middle here, what's the smallest? So just a reminder that if s is equal to f of t, is the position function, so distance is what it's talking about, then the derivative of a is the rate of change of the displacement with respect to time, so change in distance over change in time. So the derivative is the velocity of the particle at time a. The speed of the particle is the absolute value of that velocity. So velocity can go down, but speed is always positive. So let's look at a few problems. So if I give you the problem that the cost of producing X ounces of gold from a new gold mine is C equals f of x, what's the meaning of the derivative of f prime of x? And what are its units going to be? Well, the meaning is that it's the rate. So A, it's the rate at which the cost is changing per ounce of gold produced. Now, why is it per ounce? So it's producing X ounces. So whatever the X is, that's what's going to end up being the denominator. So it's per ounce, not per dollar. So cost per ounce. And what are the units? That's going to be dollars per ounce. B, what does the statement f prime of 800 equals 17 mean? So what that's going to mean is that when the 800th ounce of gold is mined or produced, the production is $17 per ounce. And C, Do you think the value of the derivative of f of x will increase or decrease in the short term? Well, probably in the short term it's going to decrease, because as you go in and mine more, then you're going to get more gold, and then your production costs go down. So it's probably going to decrease to start with. But in the long term, as you're getting less and less gold out of it, then it's probably going to increase in the long term. Another problem with a table, just so you've seen one, the table shows the value of the functions recorded every 2 hours, and it's the temperature in Dallas after midnight on June 2nd, so every 2 hours. And what's the meaning of the derivative of the temperature at 10? So right here, and then we're going to estimate its value. So what that's going to be, it's going to be the change in the temperature at 10 o'clock a.m. because it's after midnight. And so to estimate that, what we're going to do, we need to look around it and average it out. So I'm going to go the change in the temperature, 88 minus 72, over the time period. That's going to be over 4 hours. That's going to be 16 over 4, so a good estimate is about 4 degrees Fahrenheit per hour. So all the rates of change that we have looked at are derivatives and can be interpreted as the slopes of the tangent line, slopes of the tangents. So we're solving for a variety of problems involving rates of change in science and engineering. So that's all that this does. We're solving for a variety of problems involving rates of change. It can be chemical reactions over time. It can be distance over time. A lot of different things that we can solve for rates of change.